Good morning, students. Today we are going to learn about lenses and their related concepts. In this chapter, we have to learn about lenses, types of lenses, then related concepts of that lenses, sign convention, ray diagram for refracted light, working of human eye and lens, defect of vision and their correction, uses of lenses. So we'll see about lenses. What is lens? A lens is a transparent medium bound by two surfaces. The lens, which has two spherical surfaces which are proved outwards, is called a convex or double convex lens. This lens is thicker near the center as compared to the edges. The lens with both surfaces spherical on the inside is called a concave or double concave lens. This lens is thinner at the center as compared to its edges. So these are the two types of lens, that is convex lens, which is thicker near the center, and the concave lens, which is thinner at the center. Then different types of lenses. There are three types of convex lens, that is biconvex, planoconvex and positive meniscus. And there are three types of that concave lens, that is biconcave, planoconcave and negative meniscus. If you see the cross section of the convex and concave lens, you will get like this. Means the concave and this is a convex lens, which is a part of these hollow glass spheres, and this is the concave lens, which is also the part of these two spheres, in which this is the center, these are the centers, this is the radius, and these are the different parts of that lens. We'll see the different concepts related to the convex and concave lens. What of them? First, a center of curvature. Centers of spheres whose parts form surfaces of the lenses are called centers of curvatures of the lenses. A lens with both surfaces spherical has two centers of curvature, that is C1 and C2. Already we have seen the C1 and C2 are the two center of curvature. Then radius of curvature. The radii R1 and R2, which is shown in that diagram of the spheres, whose parts form surfaces of the lenses, are called the radii of curvature of the lens. So these are the radii of curvature. These are the two radii or different radii. Then principal axis, the imaginary line passing through both center of curvature is called the principal axis of the lens. Imaginary line. This is the imaginary line passes through both center of curvatures. This is the first center of curvature and this is second center of curvature from which that line is passes. So that is principal axis. You will see in this diagram also. This is the center of curvature. Here these are the center of curvature. These are the radii. Here these are the radii, and this is the line which passing through both centers of curvature, that is principal axis. Here a principal axis. Then optical center, the point inside a lens on the principal axis through which light rays pass without changing their path, is called the optical center of the lens. If you see the diagram, this is the point of the lens through which the light rays cannot change their path when passing through it. That is known as optical center of a lens. Here you will see the optical center of the optical center through which when rays passes there is no change in the direction of that rays. This is about convex lens. This is the optical center of the convex lens, and this is the optical center of the concave lens through which the rays goes directly straight without any changing direction. Then what is focal length? Focal length is the distance between the optical center and principal focus of the lens. What is focal length? Focal length is the distance between optical center and principal focus. You will see afterward what is principal focus. That principal focus is here about this lens, and for this concave lens that is here, means a distance between the optical center and principal focus of a lens is called its focal length. Then why the convex lens is called as converging lens? The light rays parallel to the principal axis falling on a convex lens comes together, that is get focused at a point on which principal axis. So this type of lens is called as converging lens. In converging lens has to collect all the rays together, and light rays parallel to the principal axis falling on a concave lens go away from one another, means those rays are diverge after refraction. So this type of lens is called divergent lens. A concave lens is said to be a divergent lens because after falling the rays on that concave lens, they go away from one another. While in concave lens, the rays which are falling on that lens, those rays are collected together, comes together. Because of that, The concave lens is said to be divergent lens and convex lens is said to be a converging lens. Then principal focus. When light rays parallel to the principal axis are incident on a convex lens, they converge to a point on the principal axis. This point is called as principal focus of the lens. If you see in this diagram, these are the rays which are parallel to the principal axis. The rays which are shown by blue color, which are parallel to this principal axis. When those rays are passing through this convex lens, they refracted, and after refraction they comes toward this principal axis on one point. That point where all these rays are come together, that point is known as principal focus of this lens. In case of this concave lens, the rays, these are the rays, after passing through this concave lens, they get diverted, means goes away from each other. A rays traveling parallel to the principal axis in a concave lens diverge after refraction in such a way that they appear to be coming out of a point on the principal axis. They appears to be coming from a single point which is on principal axis. So this point is called the principal focus of the concave lens. So the principal focus of this convex lens is on right side, and the principal focus of the concave lens is on this left side. Images formed by convex lenses. We can use the following three rules to draw the ray diagrams of images obtained by convex lenses. Out of them, first is an incident ray, which when it passes through convex lens, they get reflected and passes through a principal focus. When the incident ray, which is parallel to the principal axis, incident ray which is parallel to the principal axis, the refracted ray passes through the principal focus. This is the principal focus. Another ray, when the incident ray passes through the principal focus, incident ray passes through the principal focus, but after passing through this lens, they goes parallel to the principal focus, means vice versa of this rule. After reflection, refracted ray is parallel to the principal axis, here parallel. And third, when the incident ray passes through the optical center of the lens, this is the optical center of the lens. When incident ray passes through the optical center of the lens, it passes through this lens without changing any direction. So these are the three different rules which are useful for draw the ray diagram. So we'll see about images formed by convex lenses for different position of the object. For this purpose, you have to take the position of the object, position of the image, size of the image and nature of the image. If the object is at infinity, the position of the image will at focus f2. At that time, size of the image is point image and nature of the image is real and inverted. A position of the object beyond 2f1, the position of the image between f2 and 2f2. In the time, the size of the image will smaller. Nature of the image is real and inverted. When position of the object is at 2f1, the position of the image is at 2f2 and the size of the image is as same as object size, and this image is real and inverted. If the position of the object between f1 and 2f1, the position of the image beyond 2f2 and size of the image is larger, and nature of the image is real and inverted. If position of the object at focus f1, the position of the image at infinity and size of the image is very large, the nature of the image is real and inverted. A position of the object is between f1 and O, position of the image is on the same side of the lens as the object. The size of the image is very large and nature of the image is virtual and erect. So these are the different positions of the objects and their images. Now we'll see about images formed by concave lens. If the position of the object is at infinity, at that time the position of the image will on the first focus f1. The size of the image is point image. Nature of the image is virtual and erect. The position of the object anywhere between optical center O and infinity. At that time, the position of the image between optical center and focus f1. The size of the image is small and nature of the image is virtual and erect. So these are the different images formed by a concave lens. Then sign convention, that is Cartesian sign convention. If you see in this diagram, you will get idea about different sign conventions. That is, suppose this is a lens, this is convex lens and this is concave lens. The distance should be measured from here, optical center. Always we should measure the distance from the optical center. The distance of right side is positive and distance on left side is always taken as a negative. A distance that is upward side, that is positive, and downward, that is below, that is negative. So these are the different conventions. We will see about details about these sign conventions. According to Cartesian sign convention, the optical center is taken to be a origin. The principal axis is the x-axis of the frame of reference. The sign convention is as below. First, the object is always placed on the left side of the lens, and all distance parallel to the principal axis are measured from the optical center O. If you see here, the object should be kept at left, and the distance which is measured, which is parallel to the principal axis and starting from this optical center. The distance measured to the right of optical center are taken to be positive, while those measured to be left are taken to be negative. Then distances perpendicular to the principal axis and above it are taken to be positive, and distances perpendicular to the principal axis and below it are taken to be a negative. The focal length of the convex lens is positive, while that of concave lens is negative. Here, focal length means a length between this optical center and principal focus. So, in case of this convex lens, the principal focus is here on right side. That's why that distance is positive. And in case of concave lens, the principal focus is on left side. That's why that length is negative. Focal length is negative. Then lens formula. The formula which shows the relation between distance of the object, that is u, distance of the image, that is v, and the focal length f is called the lens formula. We will show like this. Is 1 upon v minus 1 upon u equal to 1 upon f. Then what is magnification? Magnification due to lens is the ratio of the height of the image, that is h2, to the height of the object h1. The ratio of height of the image to the height of the object, that is known as magnification. That is magnification equal to height of the image, that is h2, upon height of the object, that is h1. M equal to h2 upon h1. This magnification due to lens is also related to the distance of the object u and that of the image v from the lens. That's why we can write this magnification formula is like this: magnification equal to distance of the image upon distance of the object, that is m equal to v upon u. Then power of lens. The capacity of lens to converge or diverge incidence ray is called its power, that is P. The power of lens depends on its focal length. Power is inverse of its focal length, that is F. F is expressed in meter. Focal length here is expressed in meter. That's why the unit of the power of the, if you see the formula of the power of the lens equal to 1 upon F. F means it is focal length and which is represented in meter. That's why P equal to 1 upon F. The unit of power of lens is diopter, this is capital D, and that 1 diopter equal to 1 upon 1 meter. Then what is combination of lenses? If the powers of the two lenses are P1 and P2, then the effective power of their combination is P equal to P1 plus P2. Means when two lenses are kept touching each other, the power of the combined lens is equal to the sum of their individual powers. That is 1 upon F equal to 1 upon F1 plus 1 upon F2. 1 upon F1 means power of first lens and 1 upon F2 means power of second lens. And sum of these two lens powers of these two lens is equal to 1 upon F, the total power combination. So dear students, we'll see the next part of this topic in next period. Till that, we have to read the lesson which is in textbook and solve the exercise. If you have any doubt, you have to call me on this number or you can write your difficulties on WhatsApp. Thank you.